For decades, the search for life beyond our solar system has been a search for ourselves. We've been looking for a mirror image, an Earth 2.0, a rocky planet, just the right distance from its star, with vast blue oceans and a breathable, nitrogen-oxygen atmosphere. We've scanned the skies for a pale blue dot, a familiar beacon in the cosmic dark. But what if we've been looking in the wrong place entirely? What if the most common habitable planets in the galaxy are a thing like Earth? What if, instead of rocky worlds, the cradles of life are massive, waterlogged planets shrouded in hydrogen? Welcome to the Hycean worlds. It's a term you might not have heard before, and for good reason. It's brand new. Coined by astronomers in 2021, this new class of exoplanet has completely revolutionized our search for extraterrestrial life. The name itself, Hycean, is a simple combination of two words, hydrogen and ocean. And that's exactly what they are. Vast, globe-spanning oceans hidden beneath thick, crushing atmospheres of pure hydrogen. These are not Earth-like worlds. They are bigger, much bigger, up to 2.5 times the size of our own planet, placing them in a category we call super-Earths or mini-Neptunes, and they're hotter, too. The massive hydrogen envelope acts like a planetary-scale greenhouse blanket, trapping heat from their host star with incredible efficiency. This means that even planets orbiting far from their sun, worlds that should be frozen solid, could instead host enormous, warm, liquid water oceans. Imagine a planet that, by all old metrics, should be a dead ice ball, but is instead a vibrant, temperate water world, potentially teeming with life. This isn't just a fascinating theory. We have a prime suspect. A world called K-18b, located about 120 light-years away in the constellation Leo. This planet has become the poster child for Hycean worlds, and for a very exciting reason. In 2023, the James Webb Space Telescope, humanity's most powerful eye on the universe, stared intently at K-18b, analyzing the light that filtered through its atmosphere. What it found was astonishing. The telescope confirmed the presence of methane and carbon dioxide, key ingredients in the cosmic recipe for life. But it also detected something else, a tantalizing hint, a whisper of a molecule called dimethyl sulfide, or DMS. Now, why is that so exciting? Here on Earth, DMS has one primary source, life. Specifically, it's produced by marine phytoplankton, the microscopic organisms that form the base of our planet's oceanic food webs. The discovery of DMS in the atmosphere of an alien world is, to put it mildly, a game changer. If this detection is confirmed by future observations, it would represent one of the most significant discoveries in human history. It would be the first strong, empirical evidence of biological processes happening on another world. Of course, we must be cautious. This is a preliminary detection, and science demands rigor and repeat verification. But the possibility is electrifying. We could be on the brink of knowing we are not alone. Let's be clear, though. A Hycean world like K-18b would be no paradise for humans. Stepping onto its surface, or rather, into its ocean, would be instantly fatal. The atmospheric pressure is immense, dozens or even hundreds of times greater than on Earth. The air itself, pure hydrogen, would be completely unbreathable. It's an environment that is profoundly alien and hostile to us. But to life, that's a different story. Life is adaptable. It's tenacious. Here on Earth, it thrives in the crushing pressures of the Mariana Trench, in the boiling water of hydrothermal vents, and in highly acidic lakes. Why couldn't it adapt to a Hycean world? Imagine microbial life flourishing in that warm, pressurized ocean. Perhaps complex aquatic creatures, evolving in a world without land, could navigate its depths. Protected from harsh stellar radiation by the deep water and thick clouds, life could thrive. It might draw energy from a visible sun, but from chemical reactions in the water, a process called chemosynthesis, or maybe, just maybe, enough filtered sunlight, perhaps a dim, reddish glow, would penetrate the hazy hydrogen sky to power a form of alien photosynthesis. The concept gets even stranger when you consider a subclass of these planets known as dark Hycean worlds. These are planets that are tidally locked to their star, meaning one side always faces the star and the other side always faces away. The day side would be a scorched hellscape, with its ocean boiling away into the atmosphere, but the night side, cloaked in eternal darkness, could be a perfect haven for life. The global ocean would act as a heat regulation system, circulating warmth from the day side to the night side, creating a stable, temperate zone. Life on a dark Hycean world would never see its star. It would evolve and live in a warm, endless night, in an ocean that circles the entire planet. What kind of creatures would evolve in such a place? Bioluminescent beings, navigating by their own light in the perpetual twilight. The possibilities are mind-bending. So, why is this discovery so important? Why the shift in focus from Earth-like planets to these strange water worlds? The answer is simple: statistics. Hycean worlds are believed to be incredibly common throughout the galaxy, far more numerous than rocky, Earth-sized planets in the traditional habitable zone, and from a practical standpoint, they are much easier for us to study. Their big, puffy, hydrogen-rich atmospheres are perfect targets for our telescopes. When the planet passes in front of its star, a large amount of starlight filters through this extended atmosphere, giving us a rich signal to analyze for biosignatures like dimethyl sulfide. So, if life is common, our first definitive detection of it is more likely to come from one of these worlds than from an Earth twin. But there is a catch. A delicate balance is required. That thick hydrogen atmosphere is a powerful greenhouse agent. If it's too thick, or the planet is a little too close to its star, the effect can run away. The planet gets hotter and hotter until the ocean boils away completely, leaving behind a scorching, sterile rock, not unlike a larger version of Venus. We're not just looking for any Hycean world. We're looking for the Goldilocks Hycean worlds, not too hot, not too cold, where the atmospheric pressure and temperature are just right to maintain a stable, liquid ocean for billions of years. Close your eyes for a moment and just imagine it. You're descending into a Hycean ocean in a futuristic submersible. The sky above you isn't blue, but a hazy, swirling canvas of orange, pink, and deep purple. The weight of the atmosphere is a tangible presence, pressing down on your vessel. The water is warm, almost like a bath. As you go deeper, the alien sunlight fades, and you switch on your external lights. Their beams cut through the murky depths, and then you see it, a shadow, moving in the distance. It's large, graceful, and utterly alien. Life, not on a familiar rocky shore, but here, in the warm, dark, hydrogen-wrapped ocean of a world 100 light-years from home. The discovery of Hycean worlds has thrown open the doors of possibility. We've broadened our horizons, expanded the very definition of what a habitable planet can be. We are no longer just searching for pale blue dots. We are searching for a hazy, humid, shrouded ocean worlds. The James Webb Telescope's observation of K to 18b might be our first major clue, the beginning of a whole new chapter in our cosmic exploration. The universe, it seems, is full of water, and wherever we find water, we find hope. We find the tantalizing possibility of life. The search is on.